All right, hello Math 2200, Discrete Mathematics. It's Professor Wenson here again, going over the ZyBooks Section 1.4 on logical equivalence. All right, so we're going over what does it mean for two statements to be logically equivalent. And that's going to be when they have the same truth value, no matter what. All right, we'll see that. All right, so I'm just in section 1.4 here in your ZyBooks. Now it starts off with a couple definitions. So a compound proposition is a tautology if the proposition is always true, right? Regardless of the truth value of the individual propositions that occur in it. So a tautology is a statement that is always true, and a contradiction, right, the next bold word, is a statement that's always false. Now, the simplest examples of each of these. The simplest example of a tautology is the statement P or not P. The disjunction, right? P or not P. Because either something is or it is not, right? This is always true. And you can see the truth table here for that, where you see P or not P. The column for that is all T's. The simplest contradiction there is P and not P, right? A conjunction, and. Because something cannot be and not be at the same time, that's impossible. So you see in the truth table here, you have all F's down the column for P and not P, and I'm not going to write this out. I'll write these out though. Okay. So I have three things here. I'm not going to do all three. Right, I'll start you off. We're asked to determine whether the following compound propositions are tautologies, contradictions, or neither. So remember, tautology, always true. Contradiction, always false. And, neither would be true sometimes, false sometimes. All right, so let's start off with the statement P if and only if not P. Remember, this is that biconditional. P if and only if not P. Now, if you recall from last section 1.3, a biconditional statement was true only when the two statements on either side of it had the same truth value. Well, P's on one side, not P is on the other. Remember, not P has the opposite truth value of P. So these will never have the same truth value. This is going to always be false. And we'll see that in a truth table. But right now I know this is going to be what's called a contradiction. All right? P if and only if not P. Well, let's see that in the truth table. Now, there's only one propositional variable here. There's only one variable, P. So there's only going to be two rows. One where P is true, one where P is false. All right, I'm seeing not P show up, right? So here's not P, false, true. And then I'll make a column where we look at this statement, right? P if and only if not P. Well, in the first row, P is true, not P is false. These two statements have different truth values, so the biconditional is a false statement. Same thing here. P is false, not P is true. The two statements have different truth values, so the biconditional is false. So we're seeing always false, a contradiction. All right. So back here, a contradiction. All right, I'll leave 2 to you, and I'll move to 3. All right, so number 3 is this statement. P and Q implies P. So this is a regular conditional, just a single arrow. The hypothesis is P and Q. Conclusion is P. Now, when P is true, the whole thing will be true, right? Because remember, when when the conclusion of a conditional was true, the statement ended up being a true statement, no matter what the hypothesis was. If P is false, well, the conclusion will be false, and so will the hypothesis. You'll have false and whatever. This will be false, right? Remember, the and is only true when both are true. So this will be a false hypothesis, which will make the whole thing a true statement. This thing's always true. I can see that right now. But we'll see that in a truth table as well. Always true. That's called a tautology. Okay. So P and Q showing up here. So this can be 4 rows. Right? 2 trues, 2 falses, and then true, false, true, false. All right, now I'm going to do the one in parentheses first, right? The hypothesis. We'll do P and Q. Remember, that's only true when both P and Q are true. So true there and false every other time. And then I'll put it all together. We'll have P and Q implies P, and do the column for this. So I'm looking at this column and this column, right? P and Q, hypothesis, and this is the conclusion column. So I have true implies true, true. False implies true, true. Remember, when the hypothesis is false, the conditional statement was true. False implies false, true. False implies false, true. And you see in the end, the column for this statement has all truths. It is a tautology. All right, now you've seen other statements in the last section where some were true, some were false. You know, that's just neither. You're going to come across some things where, you know, it's not always all true or not always all false, right? You might have a mixture. Which take a look at number 2, I promise you. All right, take a look at number 2. So that's a tautology. All right, you can do the other one. All right, now what we're going to be doing with these a lot in this section is using truth tables to show that 2 statements are logically equivalent. They have the same logical meaning. Doesn't mean they have the same English meaning, just that they're logically the same. They have the same truth value all the time. So 2 compound propositions are said to be logically equivalent if they have the same truth value regardless of the truth values of their individual propositions, right? So they have the same truth value no matter what scenario you're in. And to say that 2 statements are equivalent, the symbolism for that is this like triple equal sign right here, where you have this statement right here that I just highlighted is S is logically equivalent to R, little triple equals. Okay, so they give you an example here, where again, with truth tables, you're just going to show that the columns for statements are the same. So you see here how not P has false and true down here. And then P implies not P also has false and true. So that means that not P is logically equivalent to P implies not P. And they've written that over here with the triple equal sign right here. All right, so I'll let you play that animation. And here's another thing with truth tables and whatnot. All right, so well, you know what? I'll make this one for you. All right. So say I was asked to show the following. Right. Say I was asked to show that the following 2 propositions were logically equivalent. Say that not P and not Q show that that statement is logically equivalent. That's what this triple equals means. To the statement not, and then in parentheses, P and Q. All right. So not P or not Q is logically equivalent to not P and Q. All right. So I'll make truth tables. Now the only variables that are showing up here are P and Q. So there's only going to be 4 rows again. So I'll write down here's P and Q. Usual setup, right? 2 trues, 2 falses here. and then true, false, true, false. Okay. Now what I'm going to do is I'm going to make the different parts of these. Like I'm seeing not P's and not Q's. Let's make here's not P. Now P is this column here, so not P would be false, false, true, true, right? The opposite of the P column. And I'm seeing, not Q, and not Q is the opposite of the Q column, so false, true, false, true. And then I'll keep making this statement on the left here. Now we have not P, we have not Q. Let's make the disjunction now not P or not Q. So another column, not P or not Q. And I'm just looking at these two columns here. So false or false, false, false or true, true, right? If one of them is true, it's true. If at least one of them is true. True or false, true, true or true, true. And I'm going to highlight this. I'm going to circle it, right? So this is one of the truth columns I'm focused on, right? The one for this statement. This is the truth column for not P or not Q. And if we get the same exact truth column for this statement, we'll be golden. All right. So I'm going to keep going, make more columns here. This statement over here, in parentheses, I have P and Q. All right, so I'll do P and Q. So P and Q, and I'm focusing on the P and the Q columns here. True and true, true. True and false, false. False and true, false. False and false, false. All right. And now to finish this side off, I did P and Q already. Now I'm negating that on the outside. See, it's the negation of the column P and Q. All right, so I'm negating this column, which will be false, true, true, true. And that's the column for this side. And look at them. In every single scenario, in every single row, they're the same. False, false, true, 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 true. So since they have the same truth value in every scenario, every possible scenario, they are logically equivalent. And I would write this statement up here that not P or not Q is logically equivalent to not P and Q. And in fact, this is called this is one of what's called De Morgan's laws. De Morgan's, which we'll see in a little bit. Well, that's actually later in this same section. Okay. So back here, so you saw that. All right, so participation activity. I just didn't want to write this one with 8 rows, that's all. So here, the table below shows the truth table for 3 compound propositions. So we have, P or not Q implies R. P if and only if Q, a biconditional, implies R. And not R implies not P and Q. And here they are. So number one, there's only one thing. Wow. Use the truth table to determine which logical equivalence is true. So which of these 3 statements, which pair is true? Which pair are logically equivalent? So let's see. Let's look at these first 2 here. Same, same, same. They're different here. When P is true and Q and R are false, this first statement's false, the second statement's true. So these 2 statements are not logically equivalent. How about the first and third statement? Both true in the first row, both false, both true, both false, both true, both true, both true, both false. It's the first and the third statement that are logically equivalent. So that would be this statement here. Right? The first and the third statements are logically equivalent. All right, and I just mentioned this a second ago. De Morgan's laws. De Morgan's laws are for the negation of an and statement. For one of the laws, which you saw here on my paper, the negation of an and statement, right? The negation of a conjunction, you kind of distribute the negation. You see you get not P, not Q, and then flip the and to be an or. So not the quantity P and Q is not P or, flip it, not Q. They're equivalent, as you saw here. I'll show you the other De Morgan's law, the other version of De Morgan's law. If you negate an or statement, P or Q, this will be logically equivalent, and kind of like I told you earlier. Think about, imagine distributing the negation. So I have not P and then not Q, but then the or becomes an and. Flip that middle symbol around. So this is another one of De Morgan's laws. Right? If you negate an and statement, it becomes an or statement of the negations. So another way to say that, the negation of a conjunction is the disjunction of the negations. And if you negate an or statement, you get an and statement with the negations. Or the negation of a disjunction is the conjunction of the negations. All right. And I'm going to leave it to you. All right. I showed you here. You can do truth tables. I'm going to leave it to you and make truth tables on your own. And I think they show truth tables in the book as well. But show that these are in fact also logically equivalent statements. Always have the same truth value. All right. All right. So here it is here. Right. If you negate an or statement, it's equivalent to not P or Q is equivalent to not P and not Q. And they do the other one as well. Not P or Q. The other one should be around here. It is not P and Q is equivalent to not P or not Q, and that's the one I showed you the truth tables for. All right. So let's take a look. Reasoning about De Morgan's laws. All right. So there is only one truth assignment for P and Q that make the expression not P or Q evaluate to true. Which one is it? Okay, well, I mean, you can run through these. I don't know why this would be De Morgan's, but let's take a. All right, you know what? If I go to the paper and calculator here, they gave us, the statement not P or Q, right? Again, according to De Morgan's, and you can show it with truth tables, not P or Q is equivalent to not P and not Q. All right. So remember when an and is true, right? They said, when is this going to be evaluating to true? Remember, an and statement is true when both of these are true. Well, when are both of these true? When P and Q are false, right? When P is false, this would be true because it's not P. When Q is false, this would be true because it's not Q. So when P and Q are false, then we have a true statement. You'd have true and true, which would be true. All right, same thing here. If P and Q are false, false or false is false, and not false is true. So only when P and Q are both false. And you can reason out the other one in a similar fashion. All right. And it's actually the same thing, right? Not P and not Q. All right, and we have something similar. So again, not P and Q. Right? When is that gonna be false? When is not P and Q going to be false? When both P and Q are true. Right? When both P and Q are true. And again, you can reason that out on your own if you would. I'm going to leave that to you. All right. And finally, the last activity before the additional exercises. Matching equivalent English expressions using De Morgan's laws. So select the English sentence that is logically equivalent, always has the same truth value, to the given sentence. It is not true that the child is at least 8 years old and at least 57 inches tall. All right, so I'm going to write that out on paper. Okay, so I've written out that sentence. All right. It is not true, so this is a negation, that the following, and all this is not true, right? So I'm going to put this in parentheses. The child is at least 8 years old. All right, that'll be statement P. And the child is at least 57 inches tall. That's statement Q. So what I have here is, it is not true that the child is at least 8 years old and the child is at least 57 inches tall. What I have here is this. It is not true that, again, in parentheses, the child is at least 8 years old and at least 57 inches tall. According to De Morgan's laws, this is equivalent, logically equivalent, has the same truth value as the following statement. Not P, or, all right, flip that, not Q. Now let's write this, let me write this in English. So, the child is not at least all right, so the child is not at least 8 years old. Now that's a weird way of saying that. We'll say that probably in a better way. All right, that's not P, or, all right, or, and then not Q would be, and not at least, and the child is not at least 57 inches tall. Now, what's a better way of saying that? Because not at least 8 years old. I mean, come on, nobody says it like that. Remember, at least 8 years old means 8 or more. Right? At least 8 years old means 8 or more. Not at least means less than. So the child is less than 8 years old or less than 57 inches tall. Right, again, nobody says not at least. All right, so let's go back and look and see which sentence matches that. All right, so the child is at least 8. Now the child is at least 8 years old and at least 57. That would be just P and Q. The child is less than 8 years old or less than 57 inches, shorter than 57 inches. This is the not P or not Q that I brought up. Okay? And you could do something similar for number 2. And then you have your additional exercises that show up in the weekly assignments. Right? Assignment 1 on sections 1-4 through 1-6 that you're going to be writing out on paper and uploading as a file in the assignment 1 page. I don't have every single assignment. I don't have every single exercise assigned, and you can see the solutions if you want to check yourself. I would recommend try to do things on your own first before you look at the solutions. Make sure you're actually learning something. And I didn't assign all of them, right? But I would recommend doing all of them though, even the ones I didn't assign, just to get more familiar with the material, and of course bring me questions if you have anything. All right, so that's it for 1-4 on logical equivalence, and thank you for watching.